Okay, so welcome back. So now what we're going to do is we're going to talk about the limit comparison test. So now the comparison test works really nicely if you can, one, find a series that you can compare it to, right? But second of all, that the hypotheses are also satisfied. Okay, that's the key. So for example, what if I have this series where I have the series from n equals 2 to infinity of 1 over n squared minus 1. Now, we would like to compare this to the series, right? The p series, 1 over n squared. But here's the problem. It does not satisfy the conditions because this 1 over n squared minus 1 is less than 1 over n squared. So even though this is convergent, right, we would like to show that whether this is convergent or not, but it doesn't follow the correct assumptions, okay? It would have to be oops, hold on. Oh, I'm sorry, I had it this way. This is correct. I was looking at it wrong. So this is correct. Okay? This is bigger than this for all n greater than or equal to 2. Okay? But this, in order to use the convergence, right, if this is convergent, we want to make sure that this is smaller than this, but that's not the case. So since it doesn't meet the conditions, we can't use the comparison test. But what we can use is the limit comparison test. So how would that work? Well, the way the limit comparison test works is if you have two series, n equals 1 to infinity of a sub n, and you have one to infinity of b sub n. Okay, and these are all with positive terms, right? So these are two series that have positive terms. So they're both going to be positive terms and increasing, right? They're going to have increasing partial sums. Now, what we're going to do is we're going to take the ratio of these two and take the limit of that ratio. So what we want to do is we want to take the limit as n approaches infinity of the nth terms, right? So we want a sub n over b sub n. Now, if this limit converges to some number, some real number, not equal to 0, okay? If it converges, if the limit exists and it is equal to some real number other than 0, then what can we conclude? It means that either both series converge or both series diverge. Because what's going on here is what this is telling us is as n gets sufficiently large, we can say, we're saying that a sub n is basically equal to a multiple of b sub n. Okay? And so they're either going to diverge or they're both going to converge. Okay? So if one converges, so does the other. If one diverges, so does the other. So that's where the key is. As long as we have one of these that we know whether it converges or diverges, then we can use this. Okay? So let's go back to this one. Okay, so now what are we going to do? Let's take the ratio of these two. Okay, so does it matter which one goes on top? No. Okay, but let's put the one that we're testing on top. Okay, so we'll put this one on top, so we're going to take the limit as n approaches infinity. We're going to do 1 over n squared minus 1 over 1 over n squared, which is going to be the limit as n approaches infinity of what? This is going to end up becoming n squared over n squared minus 1. And of course, as this goes to infinity, this is approaching 1, which is not equal to 0. So therefore, here's the symbol for therefore. Therefore, what? Either both series converge or both series diverge, since this is a p-series, since the series n equals 1 to infinity of 1 over n squared is a convergent p-series, the series n equals 1 to infinity of 1 over n squared minus 1 also converges by the limit comparison test. And that's it. Have a great day.